Hi, I'm Troy,
And I'm Ethan.
and this is our presentation on quantum cryptography. So, in this presentation, we're going to go over what is quantum cryptography, how does it threaten current cryptographic methods, what makes a cryptographic method quantum proof, and how does it work. So, quantum proof cryptography is where the methods used are resistant to the type of computation that quantum computers are supposedly good at. Uh, our current methods are inadequate because quantum computers are really good at certain types of problems, like prime factorization. And Shor's algorithm is an algorithm that would be used in quantum computers that is really good at doing that. So once quantum computers become more of a thing, our current basis for a lot of encryption is not going to work. So what makes something quantum proof? Well, there are several different complexity classes for categorizing problems. P, NP, NP complete, and NP hard. For classical computers, NP problems are difficult. Theoretically, quantum computers can solve some of these problems really fast. Certain problems, according to IBM and others, have yet to be proven to be easy for quantum computers.
And since we don't think they're easy for quantum computers, we've designed quantum cryptography algorithms based around these supposedly hard problems. For instance, lattice-based cryptography, symmetric key quantum resistance, multivariate cryptography, hash-based cryptography, isogeny-based cryptography, and code-based cryptography. And in this presentation, we're going to go over an example of lattice-based cryptography called the GGH cipher. So first, some definitions to know. Vectors are just going to be lists of numbers. Linear combinations are going to be where we scale and sum those vectors together. And then lattices are where we only use integer weights to combine the vectors. So we end up with these sort of black dots spaced apart by the integer weights. And then a basis is the fewest number of vectors that can be scaled to create a lattice. For instance, the blue and orange lines would represent a basis for the lattice of black dots. So in our lattice-based cryptography method, our messages are going to be weights on basis vectors. And a really hard problem for quantum computers to solve are finding the closest lattice point to something not on the lattice. And this is especially hard when the vectors are nearly parallel and they have a large magnitude. For instance, the black and pink vectors seen in the image below are very close to each other angle-wise and have large magnitudes. However, when the opposite is true, when we have short stubby vectors that are nearly perpendicular, it becomes a lot easier to figure out where this point closest to, for instance, the red vector is when we've nudged it off the lattice. So we can exploit this to make a quantum proof cryptographic method. So in this case, our private key will be 4005, which are two vectors that have a pretty small magnitude for this lattice and are perpendicular. And then we'll have our public key, 2890, 155, which have the same lattice, but these vectors are very long and close to parallel. And then we have the message 105. So what we're going to do is we're going to take our message and take the first weight and the first public key vector and multiply them together. And then we'll add on the second weight, the second weight of the message high and the second vector from our public key to get the message 7952 25635. And now if we wanted to, for instance, recover this message, we simply need to find the weights on our public key vectors that give us our message. However, and that doesn't present a problem. So what we're going to do is we're going to take this message and nudge it slightly off the lattice to get, by incrementing the top and decrementing the bottom. And what this does is if we again try and find the weights that apply to our public key to give us our message, we get a wildly different message. In this case, 114.15, 99.1, which doesn't correspond to any ASCII values because they're decimals. So to correctly recover the key, we need to use our nearly perpendicular basis to find what combination of those vectors are closest to our nudged message. And we find that to be 1988 and 5126. 1988.25 and 5126.8. And now to get it back on the lattice, we take those weights and round them to get 1988 and 5127, and now apply those back to our private key weights, or private key vectors, to obtain 7952 and 25635, which you might notice is the original weighted message that we found using the public key. So if we undo our linear combination of basis vectors, we find that the weights corresponding to our message are 104, 105, thus recovering our initial message, hi.
So, in conclusion, once quantum computers become practical to use, the cryptographic methods we use to secure our data will be really easy to break. There are methods being developed in order to prevent this from happening, and lattice-based cryptography is one of those methods.
Thank you.